Ladies and gentlemen, welcome to the elementary education of PyTorch. Alright, Christian Paul speaking once again. Okay, where we see what PyTorch is basically about. If we could basically scroll on what it basically does, it claims to be production ready, distributed training, robust ecosystem, tools and libraries, and cloud support. And they got Torch script. That might be very simple to install. Open-ended software. You can install through pip or anaconda as usual, right? So we can select any preference that you see here through numpy, however it may be, whatever build it is. And again, Python, conda, pip, libtorch, whatever source it is, and you run the command that you've shown that's down below. And they have all the projects that you definitely see with Scorts, Captum, community, all that stuff. So if we go through all the projects that we can see below, baselines, PyTorch video, glow, flare, fail scale, Clinica, paddle, deep learning, PA, pipeline transfer, deep learning, transformers, NLP, Eon knobs, powerful tensor operations, Optona, Visual, Torch IO, right? I go to page 2, Torch metrics, flower, L5 kit. All of these that you see below here, and I could go literally all the way down the list below. And verse, you see all these projects that's basically done, that's shown all the way below here. 7 pages worth, basically, ladies and gentlemen. Okay, mainly for AI, NLP, deep learning. That's what basically PyTorch is about. So if we could get started here. And how it works, we get it all set up and installation. You can definitely look at that below on pytorch.org. Now go through tutorials here, right? So we'll go through, they have an introduction to PyTorch on YouTube that you definitely look on below that deals with like a bigger detail on how PyTorch works. You can definitely go through that. So let's go through the PyTorch summary here and see how this goes, right? So we go here, get a quick start going, working with data, import, so with the code. So Torch would basically be your main code to get through Python. And they got Torch utils data loader, Torch utils data set, and data set stores the samples, and blah, 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 data loader, bracket iterable bound data set. And this is the code that you see here below, right? So you have all this code that's shown as an example, and this is the output portion that you would get here. And then the batch size, you get like a train size and a testing size, and you get your shape done with a size 64. Creating models within neural networks, they have the examples shown below, and you print the model out, and this is what it gets below. Optimize model parameters, and you get the optimizer there with a loss of a cross entropy, dealing with a training loop. Knock that out, and you would check the model's performance at that point. You do a bunch of epoch testing, and they have that shown below. You save, get that out, load the models, and then boom, you're done. Right? Tensors, you initialize a tensor, and you get a Torch tensor. They have function below. Random constant variables, attributes of it, operations, all the way down. Right, and you bridge it with numpy. All the code you see there is literally down below. Data sets and data loaders, right? And if you code for data samplers there, it can be very difficult to maintain and messy, like messy here. You know, you want the data code to be decoupled and clean as possible. Which you got Torch utils, data loader, and data sets. And to load it, you have the code that's there below. You import it, you get the import the data set that's there. You get the data sets down below, tensor below, and you get your training data set as well as your testing data set, and this is what basically loads up. And they have the sample code that's down below, what you see on your Python. And now you iterate and visualize the data set below, and they got a sample code that shows it, and it's basically a bunch of manipulative images that you see down below. And if you create a custom image data set, you get a directory on basically how the stuff is shown. An initial is there. Basically, init basically is run once instantiating the dataset object. That's what initializing is. Length function returns the number of samples in the dataset itself. Get item basically gets, loads, and returns a sample from the dataset at the given index IDX, which identifies the image's location on the disk and converts that to a tensor using read image, retrieves the corresponding label from the CSV data, and self.img underscore labels, calls the transform functions on them if applicable, and returns the tensor image and corresponding label in a tuple, and we should see that below. And now you prepare your data for training with data loaders. Dataset retrieves the dataset's features and labels one sample at a time. You train there. You get the code below with data loader and iteration that you see here. The code is there below. The image is shown and manipulated. Right? Transforms. Okay? Data does not always come in its final process form that's required for training machine learning algorithms, and transforms are used to perform some manipulation of the data and make it suitable for training. All Torch sufficient datasets have two parameters: transform to modify the features, and target transform to modify the labels, except cowbells containing the transformation logic. And you see all the code that you see here below, and you see the output that's basically there. Excuse me for the delay with loading. So toTensor is basically code on Python. You convert a pill image or numpy end array into a float tensor and scales the image pixel intensity values in the range of 0 to 1. Lambda transforms, you see that down below. You define the function and turn it into a one-hot coded tensor. Right? First creates a zero of size 10, which is the number of layers in the dataset, and calls the scatter, which assigns a value which equals 1 on the index given by the label Y. Right? Now building the neural network. Okay? Neural networks comprise of layers, last modules that perform operations on data, and they have all these namespaces that's actually shown here. If you look at the code where my mouse is pointing around there, this is how to import it, and you get the device that's there with the code, and this is the output that we'll see. Now, class definition. We define a neural network by subclassing the module and initializing neural network layers in init, which the module subclass implements the operation on input data in the forward method, in which you will see here with the code. The instance of neural network is created and moved to the device in which its structure is printed. And you see the output right there. Now, to use the model, you pass input data, execute the models forward along some background operations, and you can't really call the model.forward directly. Now, if you call the model, the input returns a 2D tensor with dim equals 0, corresponding to each output of 10 raw predicted values for each class. Dim equals 1 corresponds to the individual values of each output. So you get the predicted probabilities of passing to an instance of the NN softmax module. And this is the model that you see here below. Right? And this is the output that is shown literally below. So, using the model, passing input data, using the model forwards that's there. And you see the code that's literally down below here. And we have the model layers, and we break down in the layers of the fasten MNIST model. If in order for it to be illustrated, we'll take the sample and you pass it 3 images of size 28 by 28 and see what happens to it as you pass through the network, right? You see the code that's there below, and this is the output. Flatten, you get the layer convert each 2D 20 by 28 into a continuous array of 784 pixel values. The mean batch dimension at dimension equals 0. The code below. This will be the output size. Linear. Basically, the module applies a linear transformation of the input using stored weights and biases, which you see below, and you have the output that's there. You have the 3D features and the outs. And then review. Non-linear activations are what create the complex maps between the model's inputs and outputs. They're applied after the linear transformation includes non-linearity, helping neural networks learn a wide variety of phenomena. In the model we use, and then reloop between the linear layers, but there's other activation in this non-linearity in your model. Excuse me. And this is code that's shown. Outputs. Right there. Sequential. Order containing modules that is passed through all the modules in the same order as defined, which could be used to put together a quick network like seq modules, and you see the code below. Softmax is the last linear layer of the neural network that returns logits raw values in infinity to infinity, negative to positive, which are passed to the softmax module. The logic is stale, the values 0 to 1 representing the models predicted probabilities for each class. Then parameter clear in case of the dimension long, which the values must sum to 1. And the parameters as shown many layers inside the neural network are parameterized, which have associated weights and biases that are optimized during training. Subclassing and then that module automatically tracks all fields, define inside your model object, and makes all parameters accessible using your model's parameters or name_parameters methods. So you have an example that's coded below with the structure that's there, and this is the output that we see below. Right? So automatic differentiation with torch.autograd. When training the neural networks, the most frequently used algorithm is backpropagation. In this algorithm, parameters, model weights, are adjusted according to the gradient of the loss function with respect to the given parameter. And you got torch.autograd that's actually will show this and develop this, which supports automatic computational grading for any computational graph. So you got the simplest one-layer neural network with X, W, and B, and some whatever loss function you have below. It can be defined in PyTorch in the following manner, and you see the code below. And you see the computational graph here. X comes in the input. You got your star parameter W comes in, it gets merged up to the added distance parameter, where B comes in, converts to Z. So torch.maximum X-W plus B, right? That's where it comes from. Comes to CE. Controlled entropy creates the loss. Basically, Y goes into the controlled entropy right there, and this is what we will see here. So, a function that we apply to tensors to construct computational graphs is in fact an object class function. This object knows how to compute the function in the forward direction, and also how to compute its derivative unit during the backward propagation step. A reference to the backward propagation function stored in grad_fn property of a tensor, and you can find it in the documentation below under pytorch.org. Right? I'll put it there. Now, optimizing weights and parameters in the neural network, we need to compute the derivatives of our loss function with respect to parameters. Namely, we need the derivative, partial derivative of the loss on the W plane, and the partial derivative of the loss into the B plane under fixed values of X and Y in order for these derivatives can be computed. So you use the logs for a backward function, and then retrieve the values from w.grad and b.grad, basically the gradients of both these parameters here. And this is the output that we see. Alright, and you have the notes there. Now, disabling the gradient tracking, so by default, our tensors with requires _grad equals true are tracking the computational history and support gradient computation. However, there are some cases where we do not need to do that. For example, when you have trained the model and just want to apply some input data. For example, you want to do forward computations through the network. We can stop tracking computations by surrounding our computation code with torch.no_grad block. And you see the code below, and the requirements basically give the output of true or false. In order to get the same results, you use the attach method on the tensor, and same code gives the output false, right? So the previous one, the top one deals with the torch. Top one represents true. Now you have the no grad, same thing, false, false. Now there are reasons you may want to disable gradient tracking. To mark some parameters in your neural network as frozen parameters, which is very common for fine-tuning a pre-trained network, and the speed of the computations when you're only doing the forward pass, because computations on tensors that do not track gradients will be more efficient. Now, computational graphs. Conceptually, AutoGrad keeps a record of data, tensors, and all executed operations along the result new tensors, and a directed acrylic graph, DAG for short, consisting of functional objects. And this DAG, leaves are the input tensors, roots are the output tensors. By tracing the graph from roots to leaves, you can automatically compute the gradients using the chain rule. In the forward pass, AutoGrad does two things simultaneously: run the request operation and compute a resultant tensor, and maintain the operations gradient function in the DAG. The backward path kicks off when the backward function is called in the DAG root. AutoGrad then computes gradients from each grad fn, accumulates from the respective tensors .grad attribute, and using the chain rule, propagating all the way to the leaf tensors. And you got your optimal reading in tensor gradients and Jacobian products, and this is basically engineering math at its pure form, or applied mathematics in its pure form. So in many cases, You have a scalar loss function, and we need to compute the gradient with respect to some parameters. However, there are cases when the output function is an arbitrary tensor. In this case, PyTorch allows you to compute the so-called Jacobian product and not the actual gradient. For the vector function y hat, y underscore arrow with f of x underscore arrow, where x hat is, this little vector here, and y hat is this little vector there, within those functions, and then respectively. The y gradient with respect to the x gradient is given by this Jacobian matrix, which are a bunch of partial derivatives that you see below. And for the folks that actually have the advanced 10 degrees, y'all know what I'm talking about. But don't worry, you actually dig more into PyTorch.org and into probably deal with some more further advanced calculus up in YouTube for more understanding if you're further interested. Right? So instead of computing the Jacobian matrix itself, PyTorch allows you to compute the Jacobian product, which is like the tensor, right? The tensor vector dot j for a given input vector of v1.vm having b, which is achieved by calling the backward v as an argument. The size of v should be the same as the size of the original tensor with respect to which we want to compute the product. And this is the code that we see here. And this is the output that is actually shown. Now notice that when they call backward for the second common same argument, second call, the value of the gradient is different. You're seeing a double. This happens because doing backward propagation, PyTorch accumulates the gradients, right? But it's called original. Second called doubles, right? So you're accumulating the gradients. So value computed gradients is added to the grad property of all leaf nodes of the computational graph. Now, if you want to compute the proper gradients, you have to zero out the grad property before. In real life training, the optimizer helps to do this. Now, once these are zeroed, you're back to the first call, right? And this is how this stuff is done, right? Optimizing model parameters, okay? Now that we have the model and the data, it's time to train, validate, and test the model by optimizing the parameters on the data. Train the model is an iterative process. In each iteration, the model makes a guess about the output, basically plays chess in a way, calculates the error in its guess, collects the derivatives of the error with respect to the parameters, as seen in the previous section, and optimizes these parameters using gradient descent. And they have a more detailed walkthrough of this process. You can actually click on this link here, right there. Now we load the code that's shown, and you build the model, and you see all this code that you can definitely copy and implement in your system here. And this is your model that actually comes out with the output below. Now you have your hyperparameters. Okay. The hyperparameters are adjustable parameters that let you control the model optimization process. Different hyperparameter values can impact model training and convergence rates, and they have a link which actually dig more into hyperparameter tuning, which you could look under PyTorch.org, which will define the hyperparameters for training. Number of epochs, number of times array over the data set. Batch size, which is the number of data samples propagated through the network before the parameters are updated. And learning rate, which is how much to update models parameters at each batch/epoch. Smaller values yield slow learning speed, while large values may result in unpredictable behavior during training, and you see the code here below. The optimization loop, once the hyperparameters are set, they can be trained and optimized with the model with optimization looped. Each iteration of the optimization route is called an epoch. Each epoch consists of two main parts. The train loop, which iterates over the trained data set and try to convert to the optimal parameters, and the validation/test loop, which iterates over the test data set to check if the model performance is improving. That's why you see a bunch of all these data with like the CSV forms of train and test. So let's familiarize ourselves with some of the concepts used in the training loop, and we'll jump ahead to see the full implementation that's shown below if we choose to actually click that link. Loss function, when presented with some training data, our untrained network is likely not to give the correct answer. The loss function measures the degree of dissimilarity of obtained results to the target value, and it is the loss function that we want to minimize during training. To calculate the loss, we make a prediction using inputs of our given data sample and compare it against the true data label value. Right, common loss functions include nn.msc loss, which is the mean square error for regression tasks, and nn.nl loss, which is the negative log likelihood for classification. And then cross entropy loss combines nn.log softmax and nn.nl loss. And and you pass the models output logic to nn.cross entropy loss, which will normalize the logics and compute the prediction error. You see the code up there. The optimizer. Optimization is the process of adjusting model parameters to reduce model error in each training step. Optimization algorithms define how this process is performed, and we'll use this category in this end in the example. All optimization logic is encapsulated in the optimizer object, in which the SEG optimizer is used. Additionally, there are many different optimizers available in PyTorch, such as Atom and RMS prop, that work better for different kinds of models and data, which could vary. The optimizer is initialized by registering the models parameters that need to be trained and passing the learning rate parameter. You see the code right here. Inside the train loop, optimization happens in 3 steps. Call optimizer.0_grad to reset the gradients of the model parameters. Gradients by default add up. To prevent double counting, we explicitly zero them in each iteration. Propagate the prediction loss with call to loss backward, and you got the parentheses there. PyTorch supplies the gradients of the loss with respect to each parameter, and once you have the gradients, we call optimizer step to adjust the parameters by the gradients collected in the backward pass. Now you have the full information of the code. You find the training loop that loops over the optimization code, and the test loop that evaluates the model's performance against the test data. So this is the code you see below here. All of it that's shown with the training loop, and below you see the testing loop that's down. Now the loss function is initiated, and the optimizer is also initiated, and it's passed to both the train loop and the test loop. And you can trace the number of epoch shots and models improving performance that's actually shown. It can go from 10 to 100 and see the outcomes, and you print them all out. Right, this is the outcome. Boom. Right there. Efficiency is actually minimized. Boom. 38% at 0.7% accuracy. Right, average loss 2.16. Epoch 2 all dropped out. This one is at 52% accuracy, 188. Third epoch, you see here the loss that's there, 60%. Fourth epoch, and you notice the accuracy starting to improve more and more and more and more using these methods. Okay, now saving and loading the model is going to be the last step, right? So you import the torch and you import the models here, and you save and load the model weights. You use the state-dict function and the torch.save method, and this is how you definitely get all the models saved within that system. And this is the output, and this is how it loads up, and then boom. Now if you want to load the model weights, this is the code to actually do that, and you load the same model weight that's saved. Boom, boom, right there. And if you do the save and load models with shapes, this is your code below to save. This is your code to load. Alright. So, for more information, ladies and gentlemen, about PyTorch, you can go check out pytorch.org, and then you'll be able to actually explore all of the pages and as well as the links on what the site brings. With that, Christian Paul from the Nerd Chronicles is signing out. Deuces, deuces, deuces.